Toroid is a hollow circular, it is a solenoid only, solenoid in the shape of circle. It is solenoid but it is in the shape of circle. It is having large number of turns. It will be looking like this. These are loops. Okay, the solenoid we have converted into a circle. It's a spring in the form of circle. That is toroid. We are going to consider a toroid. This is our toroid. Okay, it is a solenoid in the form of circle. Okay, and we are going to find the magnetic field due to toroid. So there are 3 points. There are 3 points. One point is, this is the radius of this toroid, it is r. Radius of this circular toroid, circular solenoid, it is r, and we are considering 3 points. One point is outside the toroid, okay, P outside. One point is inside the toroid, P inside. One point is within the toroid, P within. And like our previous derivation, consider a toroid of turn density n. A current I is passing through the toroid. So we are considering this. There is a toroid. The turn density of toroid is n. Turn density means number of turns in unit length. Okay. So first we are going to find magnetic field B outside the toroid. For finding the magnetic field, the first step, what is the first step? So we need to consider an Amperian loop. That Amperian loop should pass through that point. So we are considering that Amperian loop. The radius of that Amperian loop is small letter r. Okay, this is my Amperian loop. This is our Amperian loop. What's our equation according to Ampere's circuital theorem? B dot dl equal to mu 0 I. B dot dl. Angle is always 0. Okay, that's why I am not writing this B dot dl, B into dl. It will be always B into dl. We need to consider an Amperian loop. In this Amperian loop, the angle between magnetic field and dl should be 0. Okay, B into dl equal to mu 0 I. Now we are considering this Amperian loop. We are going to find total current inside the Amperian loop. I equal to, this is my Amperian loop. What is the total current inside the Amperian loop? We are considering total toroid. Okay, total toroid. So I am going to draw the toroid here. I am going to draw one section of toroid, and this is my Amperian loop. This is my Amperian loop. We are looking from a side. This is view from the top. I am looking from a side. From a side. This is my Amperian loop. Okay, circle. And the toroid is like this. Half is here. One side, okay. And other half, it's like this. This is the toroid. And we have considered the entire toroid, but this is one part of the toroid. Here, this current is coming out, this current is going in, this current is coming out, this current is going in, this current is going out, coming out, going in, going out, going in, coming out, going in. So when we are considering the total current through this plane, okay, the total current will be 0, because how much current is going in, that much current is coming out. So total current in this loop, it will be 0. So when we are considering, in the previous case, solenoid, we have considered an Amperian loop, and this is the Amperian loop, and we have considered only half, because if I am considering the full solenoid, then total current will be 0. I is going in, I is coming out. So I1 minus I2 we need to take. Similarly, current is going in, current is coming out. So we need to take the difference. One current will be plus, other current negative. Plus current, minus current, plus current, minus current, plus current, minus current. So total current will be 0. Okay. So when we are considering a point outside the toroid and we are considering the Amperian loop, in the Amperian loop, all of the toroids are part of this Amperian loop. Because of that, this plane is having incoming current and outgoing current, and it is in, one current is going into the plane, other current is coming out of the plane. So total current will be 0. Okay, so here the total current is 0 because incoming current, one current is going in, one current is coming out. So total current is 0. So we can write I equal to 0. If I equal to 0, then net current is 0. I equal to 0. Integral B dot dl equal to 0. B into dl. This dl, it cannot be 0 because there is an Amperian loop. dl cannot be 0 because there is an Amperian loop and there is a small length dl. So when we are integrating, we are going to get 2 pi r. It cannot be 0, but B can be 0. So from here, only option is B equal to 0. So magnetic field outside the toroid, it is 0. So the first point, it's done. Okay, now the second one. Magnetic field inside the toroid. We are going to do with the point, we are considering the point inside the toroid. Okay, magnetic field B inside the toroid. So this is the point P inside. Okay, this is the point P inside. First, what we need to do here, we are considering Amperian loop. We are considering an Amperian loop. Okay, consider an Amperian loop along P inside. This is my Amperian loop. Okay, what will be the total current inside the Amperian loop? 0. It will be 0 because inside this Amperian loop there is no turns, there is no current. Okay, it is inside the Amperian loop, there is no turns, there is no any of the part of this toroid is not included in this Amperian loop. So we can write I equal to 0. If I equal to 0, the same step, net current is 0, integral B dot dl is equal to 0. Integral dl cannot be 0 because there is a radius, there is integration, and but B can be 0. So only option is B equal to 0. Next one, magnetic field within the toroid. This point P within the toroid. The first step is considering an Amperian loop. We are considering an Amperian loop which is exactly half of the toroid, right? So when we are finding the total current, we will get a current. If I am considering a loop which is including all the toroid, then total current will be 0 because incoming current and outgoing current. Here we are considering bottom only the bottom. So all the current will be in same direction. Okay, it can be minus I or plus I. All the current will be in same direction. So there will be one current. Okay, so this is my Amperian loop. So we have considered only half, there will be a current. Okay, current in one turn is I. If the current is one turn, half turn, it is I. Then the current density, turn density is N. And what will be the length of this loop? What will be the length of this loop? 2 pi r. The length of this Amperian loop will be 2 pi r. So we can write total current will be I equal to N into 2 pi r I. Number density, turn density into length into current. Current in one turn is I and total current in length 2 pi r is N into 2 pi r I. Okay, now we got current, total current. Now we can apply our Amperian circuital theorem, Ampere's circuital theorem. Integral B dot dl equal to mu 0. Instead of I, we can give this N into 2 pi r I. Instead of this I, we can give this because this is the total current. So mu 0 N 2 pi r I. Now integration, B we are taking out. It will be B into integral dl is equal to mu 0 N into 2 pi r I. What is, if dl is small length here, it is dl. When we are integrating it, we will get total length, that is 2 pi r. R is radius. So B into 2 pi r equal to mu 0 N into 2 pi r I. Terms, there are common terms, 2 pi r and 2 pi r, they are common, so we can cancel it. So the remaining term will be B equal to mu 0 Ni. So both equations are same. If it is toroid, if it is solenoid, the magnetic field will be mu 0 Ni. And in both case, outside the toroid there is no magnetic field, inside the toroid there is no magnetic field, only in the toroid, within the toroid there is a magnetic field. In solenoid also, outside the solenoid there is no magnetic field, only in the solenoid there is magnetic field.